Yeah, thank you. If anybody else wants to record also, please let me know. Okay. So, okay, so coming back to this integral, so all we have done is basically substituted 2me in this expression by using the formula coming from epsilon, and you write down everything in terms of epsilon and get rid of e. Okay, and you get an expression which is like this. Okay, good. Now we will integrate by parts and write down, just take this derivative on this cos and write down this expression in this particular fashion. Fine. So after that, we just do partial fraction. That means we just add 1 plus, we just write down this as 1 plus epsilon sine omega minus 1, and 1 plus epsilon sine omega gives you this factor, and minus 1 gives you this factor. Okay, that is the usual partial fraction thing. Okay. And now we will change the variables. We write down z is equal to e to the I omega, and use this to rewrite this entire integral. Okay, so if you write down z is equal to e to the I omega, then sine omega would be z minus z inverse upon 2i. Okay, so that is the kind of expression that we will use here. So this quantity up to this overall factor, which I have kind of ignored out here, but up to this overall factor, you get this integral to be integral of this quantity. I'm sorry, the integral sign is also missing. Okay, and you can manipulate this expression a bit, and you will find that the iz factor would get cancelled out when you kind of expand this bracket, and you get an expression which is like this. Okay, now all you have to do is to pick up poles from this expression and do contour integral. Okay, fine. So let me kind of temporarily remove this stuff. Okay, so the expression in the denominator has poles located at these 2 points. Okay, and we want to therefore pick contribution from these poles. Now, of course, if you choose a contour which goes around both the poles, answer would be 0, simply because you can just take it out from infinity. You can check this integral has no singularity at infinity, and therefore the answer would be 0, which just means that the contribution coming from these 2 poles is equal and opposite. Okay, so what you need to do is to choose your contour correctly, and that is some exercise that you can do, but in fact I will give that as an exercise. But if you do this contour integral correctly, you get the answer which is like this. Okay, so here's an exercise that you can carry out this contour integral. Again, I forgot integral sign here because I have just copied it from there. And when you do this integral, you get expression like this. Choose the contour which goes around z is equal to this quantity in a clockwise manner, or choose a contour when z is equal to this quantity in the counterclockwise manner. In other words, you choose the original integral contour to be z is equal to some real part minus I epsilon. Okay, a line which is parallel to the real
So
axis. Yeah.
I was saying that we defined z as e to the iota omega.
Yeah.
That and the integration variable was omega, so somewhat a 0 to 2 pi interval, right?
That is right. Yeah.
So z is varying on a unit circle.
Yes, indeed.
So one of the roots is outside, isn't it?
Yeah,
Like,
yeah, exactly. So that is the point, that because one of the roots is outside, you could, either you integrate. Okay, just let me have it on the screen. Either you kind of pick this pole and integrate along the contour that you would get as a unit circle, or you could pick this which is outside the unit circle and deform the contour and do the integral in the clockwise manner. You understand what I'm saying?
yeah, but we don't need both the roots. Like
Oh, you don't
we
need at all.
only,
You need only one of them. If you
yeah,
take both, answer is 0 actually.
yeah,
Okay. So I'm saying that like this or this. Okay. Any one of the thing that you could choose. Okay.
yeah. Okay.
So if you do that, you would get this answer. Okay, so that is the answer that I have stated out here. Okay, fine. So what we want to do is to substitute this answer in the Sommerfeld relation. Now, Sommerfeld relation was NH prime. Remember, it was uh, so this quantity that we are trying to evaluate. Okay, let me stay wherever I am and split the screen. Okay. So the relation that we were trying to look at was this. Okay, PR dr, that would give you an expression which is n prime h. Okay, but that expression was sorry. Okay, uh, this is the left hand side, but this expression was written as PR squared r squared upon p omega times d omega integral, and we manipulated this integral. Okay, when we manipulated this integral, we encountered two terms. Okay, one of them was minus 2 pi L plus L times this quantity. Okay, so all I'm trying to state here is that you get n prime h is equal to minus 2 pi L times whatever is the answer that we got just now, which is this expression. This expression, of course, has a L sitting outside. So just want to kind of show it again. There's a L sitting outside. So you use that relation and you get 2 pi L upon square root of 1 minus epsilon squared. Okay. So now you can pull this quantity on the other side. Remember, L was same as h bar times k in the way the quantization rule was defined. Okay. So you get this, and this is a radial quantum number, this is angular quantum number. And so therefore we should actually be calling this as a principal quantum number. Okay, that quantity is L upon square root of 1 minus epsilon squared. Okay, again use whatever is the value of epsilon that we had looked at. Okay, substitute up there, you get this relation. If you invert, you get the hydrogen atom spectrum. Okay, where of course n prime plus k would be the principal quantum number. Okay, now of course one could do a little more detailed computation and get that 3 by 8 minus whatever factor that we had, also using the Sommerfeld formula, but that would take much more time actually. One could do the same computation even for the relativistic case, because if you remember that the relativistic problem and non-relativistic problems were related by just shifting the parameters of the theory. Okay, so if you replace wherever you have mze squared by ez squared and L into L plus 1 by L into L plus 1 minus some other factor, some z squared upon something. If you do those shifts, then you can carry out exactly same exercise. Okay, and you should be able to get the relativistic spectrum that we obtained, namely mc squared divided by some square root of a quantity, which is like 1 plus whatever z squared upon some number. Okay, I don't remember exact form of that right now. Okay, so even that can be completely derived using both Sommerfeld quantization rule. Okay, fine. So what we'll do is we'll leave this topic at this point. In principle, a similar exercise with square root for a relativistic problem can be done even for the using this technique even for the relativistic problem. Okay, so what we'll do now is to switch over and look at the Dirac equation. Okay, so let me close this right now because I don't need this bit. Okay, so Dirac wanted to get rid of the sign ambiguity in the dispersion relation because remember E squared was P squared C squared plus M squared C to the fourth, and so if you want to write down energy, you always ended up with getting plus or minus sign in front of the square root. So one way he thought he could do this is to write the equation in the first order time derivative form. Okay, which is a natural thing that you would think, because if you have first order time derivative, you directly get energy and you don't get E squared. So he assumed that he would write down E to be alpha dot P times C plus beta times MC squared. Okay, and of course impose relativistic invariance on the dispersion relation written in this particular form. Okay. Now, of course, he immediately realized that he can write down an expression like this only if alpha beta are matrices. Otherwise, he wouldn't be able to write down this expression in the first order form and still maintain that the relativistic invariance would require p squared and m squared c to the fourth kind of term. Okay. But what should be the form of alpha and beta is not immediately obvious by looking at this, but it is not difficult to derive that. Okay. So the first thing he considered was impose the condition that E squared gives you the relativistic dispersion relation, and but the E is of course defined in terms of alpha and beta, so you have to square this object. Okay. So as soon as you square this object, you encounter various kinds of terms. Because you have to write alpha I pi times alpha j pj, and if I is equal to j, then of course you get alpha I squared kind of piece, and alpha I squared times p squared. But if I is not equal to j, then you need to ask question, what is the meaning of pi pj kind of piece, which of course is not there in the relativistic expression. So you impose those conditions. You say alpha I alpha j plus alpha j alpha I is equal to 2 times delta ij. That is what would give you p squared c squared. And beta squared equals 1 will naturally give you m squared c to the 4. Then of course there are cross terms, and that also you'll have to set them to 0. Here also of course because of delta ij, cross terms are essentially 0. Okay. So if you use these constraints on alphas and betas, then square of this first order dispersion relation produces the relativistic equation that we have. Okay. Fine. But given the fact that these objects seem to anti-commute, okay, alpha I alpha j plus alpha j alpha I is equal to 0 if I and j are not equal to each other, is a natural kind of case for alphas being matrices. Okay, because if alphas were just numbers, this would never happen. Okay, so that is one clue of them being matrices. Okay, fine. So even for the matrix algebra, this kind of expression was not new. We know that polymatrices would satisfy an equation of this kind. But the problem is that we don't have only three alphas. Ij already take three values, 1, 2, 3. But we want four matrices like this. Okay, beta also has to have this property that, that beta alpha plus alpha beta should be equal to 0 and beta squares to 1. Now, of course, this expression also tells you that alpha squares to 1. Okay, so therefore that is the condition that would be satisfied by polymatrices, but we have only three polymatrices. Okay, now of course one could write down identity as the fourth matrix, but identity matrix would not transform in this particular fashion. Okay, so alpha I times identity plus identity times alpha I wouldn't be 0. Okay, so clearly you need a fourth matrix, and in the 2 by 2 matrix algebra you don't have more than three matrices of this kind. Okay, which essentially means that you would have to look at matrices which are larger than 2 by 2 matrices. Okay, so let's try to figure out what should be the size of the matrix such that it would satisfy the constraints that we have, namely these three equations. Okay, so any questions here? Okay. Okay, so if there are no questions, let's go ahead. So Dirac generalized the polymatrices to higher dimensional matrices, which would satisfy the conditions that we looked at. Okay, so to be able to do that, let's write them in a little more covariant form. Although this is not the best form that we would want to look at, but nevertheless, let's write them right now in this form. That we write down a 4-vector alpha mu, whose zeroth component is beta, and first, second, and third component is alpha 1, alpha 2, alpha 3. Okay, if you do that, then these three relations that we have written down can be written in terms of single covariant equation, which is alpha nu plus alpha nu equals 2 delta mu nu. Okay, this algebra is called the Clifford algebra. Okay, and one wants to basically look at the representation theory of this Clifford algebra to determine what kind of solutions to Dirac equation that one can get. Okay, and remember one thing, that after having written this in a covariant form, you could actually liberate the number of values that mu nu can take. Okay, you could say that like mu nu take values say 0, 1, 2 only, or 0, 1, 2, 3, which is the 3 plus 1 dimension space time, or you could say it can take value 0, 1, 2 dot, 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 all the way up to say d minus 1. Okay, which is like a d dimensional space time. Okay, for any d. Okay, and for each such d, okay, whatever algebra you would get would be called the Clifford algebra in that dimension, and representation theory of that Clifford algebra would tell you what is a kind of form of what is the form of solution to the Dirac equation. Okay, fine. Now remember, Clifford algebra, I have defined it in this particular fashion, but it is not necessary that the right hand side should necessarily be delta mu nu. It could be any metric there. Okay, and of course, when I say any metric, I don't really mean. I'm not talking about say general relativity where you write down g mu nu x or some such thing. That would be a bit complicated stuff. In fact, one doesn't do study fermions in that fashion, but that is a separate thing. Right now, what I meant was that right now you get alpha nu plus alpha mu equals 2 times delta mu nu, but it may be better if we could write down matrices such that this quantity is, instead of delta mu nu, it is eta mu nu, which is a Minkowski matrix. Okay, which will naturally carry the Minkowski or the Lorentzian signature of space-time. Okay. Okay, so we'll come to that as we proceed. Okay, fine. So besides realizing that they should be matrices and they should satisfy this Clifford algebra condition, we also need to impose some additional conditions on these alpha and beta matrices or alpha mu matrices. Okay, and so let's look at these physical constraints that we have. First thing is that when you look at this dispersion relation that Dirac has written down, and you want to elevate this dispersion relation to an operator equation, okay, operator relation, then you would say that E is uh, an eigenvalue of an Hamiltonian. Okay, so you put Hamiltonian on left hand side. A P vector would be eigenvalue or expectation value of a momentum operator, and once you do that, then you can interpret this as a operator equation where you write down Hamiltonian in terms of momentum operator and the rest energy piece. Okay, so if you do that, then in that case you have to ensure one thing, that energy spectrum is real, and because it is real, you have to ensure that the Hamiltonian that you write down is a Hermitian operator. Similarly, if you are studying say free particle problem, then the momentum that you are studying is a good quantum number, and therefore the momentum operator should be Hermitian. Okay, and generically the momentum operator would be Hermitian even if the particle is interacting. Okay, so you need to impose this hermiticity conditions on these operators. Okay, now clearly you have alpha. Sorry, clearly you also have alpha matrix sitting around with P. And if you impose hermiticity condition, then that reflects onto the hermiticity condition on alpha and beta. And what we find, that entire set of alpha mu matrices should be Hermitian, such that the Hamiltonian would be Hermitian. Okay, fine. Now remember that alpha I alpha j or alpha mu was giving us 2 times delta mu nu, implies that if mu is equal to nu, which means alpha square, that would give you 1. Okay, but if alpha square is equal to 1, okay, that means your matrix would have eigenvalue plus or minus 1, given that alpha mu is Hermitian. Okay, that essentially fixes your eigenvalues to be plus or minus 1, so that when you square that matrix, it will give you 1. Okay, In addition to that, you could ask what is the trace of the matrix. Okay, so you take the trace of alpha, say alpha I, then trace of alpha I, remember beta squared is 1, right? Beta squared is 1. So we could use that, and you can add, you can multiply by beta squared, which is like multiplying by identity matrix. So trace of alpha I is same as trace of alpha I times beta squared. Okay, but we know alpha I beta is minus beta times alpha I. Okay, that is the third equation that we have. Alpha I beta is minus beta alpha I, right? So if you use that, then you can swap one of the beta across alpha I and you get this expression with a minus sign. Okay, you can pull the minus sign out of this trace if you wish. Okay, then you get the expression which is beta alpha beta, and you are taking a trace of that. But remember, the trace is independent of the order in which you write down matrices, as long as that order is only cyclically permuted. Okay, so in other words, you can cyclically permute this and write this expression again as alpha I beta squared. Okay, but now you have a minus sign. So it tells you that trace of alpha I is same as trace of minus alpha I. Okay, so only answer to this is that alpha I must be a traceless matrix. Okay, so what we have now is that you have set of matrices whose eigenvalues are plus or minus 1. Okay, and the matrix is traceless. Okay, and of course the matrix squares to 1. So one thing that you cannot do, for example, is that since you cannot use 2 by 2 matrices because we have already exhausted poly matrices and we wanted 4 matrices, you could have thought that you would probably use 3 by 3 matrices. Okay, if you try to use 3 by 3 matrices, then you would encounter a problem, because if the trace of the matrix is 0, then and the eigenvalues are plus or minus 1, then there is no way you could write down a 3 by 3 matrix which would satisfy that condition. Okay, now you may say that, like, okay, one eigenvalue is plus 1, one eigenvalue is minus 1, third could be 0. Well, that wouldn't be correct, because the matrix squares to identity. Okay, so therefore all the eigenvalues should be non-zero. Okay, fine. So from that we learn that alpha must be even dimensional matrix. Okay, so if it's an n by n matrix, then n is an even number. Okay.
Sir,
Yes.
sir, how did we get from second to third step?
From here to here.
Yes.
See, okay, just hold on. Okay, so can you see this alpha beta matrix relations?
Yes.
Okay, so now let's try to apply it to this. Okay, so we have a trace of alpha I, and we write that as trace of alpha I times beta squared. That is kind of trivial thing to do, because beta squared is just 1. Okay, it's identity matrix, so it wouldn't, multiplying any matrix by identity matrix cannot change the trace, right?
Yes.
Okay, so now we write this expression as alpha I times beta times beta. Okay, beta squared is just product of 2 betas, right? Now we look at alpha I times beta and use the fact that alpha I times beta is equal to minus beta times alpha I, right?
Yeah.
So I replace alpha I beta by minus beta alpha I and keep the third term, or the second beta, on the right hand side. Is that okay?
Yes. Yes. Okay.
Fine. So now trace has a cyclic property, right? I can cyclically arrange these matrices without changing the trace.
Yes.
So I take the left beta around to the right, and I get this expression back, except with a minus sign.
Yeah.
Right? But beta squared is 1, so therefore you get trace of alpha I is equal to trace of minus alpha I. Is that okay?
Yeah. 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 Okay. Thanks.
Okay, so this tells you that this equation would be valid only if the trace of alpha is just 0. Okay, if it is 0, then it is minus of itself. Okay.
Yeah. Okay.
Now, of course, you can do the same exercise with beta matrix also. There is nothing very special happening. All you do is replace alpha I by beta and replace beta by alpha I squared. Where alpha is squared, alpha also squares to 1 from this relation. Okay, and if you do the same exercise, you will find that beta also is a traceless matrix. Okay, so eventually what we learn is that all components of alpha mu are traceless matrices with eigenvalues plus or minus 1. Okay, and that tells you that alpha mu must be even dimensional matrix. Okay, one important thing about this is that all these properties that we have written down, we did not make any specific choice of alpha matrix or beta matrix to arrive at these results. Okay, so therefore these results are independent of choice of basis. Okay, the reason for saying this is because when we write down alpha and beta matrices, there are multiple ways in which you could write down these matrices. There is nothing called a universal choice. Okay, there is definitely no unique choice. Okay, but there is not even a universal choice. Okay, so there are multiple different representations, and any choice of basis is as good as any other basis. Okay, provided of course it satisfies this constraint. Okay, and automatically kind of satisfies all these plus minus 1 eigenvalue and the tracelessness condition. Okay, any other question? Okay, so let's go ahead. The question is, what should be the dimensionality of these matrices? And this question has answered that dimensionality of these matrices depend on the space-time dimensions in which you are trying to solve this equation. Okay, so first thing that we noticed was that if we are working in 4-dimensional space-time, okay, 3 space and 1 time, then these matrices cannot be 2 by 2 matrices. That is one thing that we learned. Okay, but there could be 4 by 4 matrices, 6 by 6 matrices. How do we decide as to what should be the correct dimension? Okay, now this is the thing where Clifford algebra gets back in, and the Clifford algebra representation theory actually tells you what should be the size of the solution to the Dirac equation, or what should be the dimension of the alpha and beta matrices appearing in the Dirac equation. Okay, and the answer is that if you are in d space-time dimensions, that means d minus 1 space and 1 time direction, then we need 2 to the d by 2. The square bracket means that, remember, d could be any number, it could be even or odd, right? So d by 2 may not be an integer. Okay, if d is even, of course it is an integer, but d odd, it won't be integer. The square bracket tells you that you take integral part of it. So for example, if d is equal to say 5, then 5 by 2 would be treated as 2. Okay, it's like that. Okay, uh, so what the Clifford algebra representation theory tells us is that if you are in d space-time dimensions, then we need 2 to the d by 2 integral part of that dimensional matrices to write down the equation of motion for a massive particle. Okay, on the other hand, if you are studying massless particle, then you don't need that size matrices. You need a matrix which is 2 to the d minus 1 by 2. Okay, so they are smaller matrices. Okay, so for example, if you take d is equal to 4, which is the space-time dimension in which we would be working throughout this course, then you find that for the massive Dirac particle, you would require 4 by 4 matrices, because d by 2 is 2 and 2 to the 2 is 4. Okay, so you need 4 by 4 matrices. But if you are studying a massless particle, then d minus 1 by 2 is 3 by 2, whose integral part is 1, and therefore you would need actually 2 by 2 matrices. Okay, so we do have both the representations. We write down 2-component formulation as well as write down 4-component formulation, and clearly you need 4-component formulation for massive particles. You could, if you wish, you could write down 4-component formulation for massless particles, but it's kind of a lot of redundancy. You don't have to do that. You can write it in terms of 2-component formulation. Okay, so So it kind of immediately follows from what I just said, that if you realize that alphas and betas are matrices of specific dimensions, then the corresponding solution to this equation would have that many, would be a column vector with that many component. So if it is 2n by 2n matrix, then psi would have 2n components. Okay, so therefore psi is a multi-component wave function, and it will be called spinor. Okay, that is, so solution to this equation is called spinor. Okay, so what we will do now is to modify the form of the equation so that we can write it in a covariant form. Right now, this equation doesn't look very covariant. Okay, by the way, this equation is called the Dirac equation. Okay, but of course, Dirac also wrote it down in the covariant form. So that's why I would mention the name Dirac equation in the covariant form. So what we will do is we first of all we see that this equation is the first order in time derivative as well as first order in spatial derivatives. Okay, but there are matrices multiplying the spatial derivative and no matrix multiplying the time derivative. Okay, now you can remedy this thing by, so that you can try to bring this equation into a covariant form, relativistic form. Okay, by multiplying this entire equation by beta. If you multiply by beta, then beta squared here will kind of be equal to 1 because of this condition that beta squares to 1. Okay, and you would have a beta sitting out here. Okay, now once you have a beta sitting here and a beta times alpha sitting here and identity matrix sitting there, we could redefine this to new set of matrices, and we call them gamma 0 is equal to beta and gamma I is equal to beta times alpha I. Okay, now notice that I have used index upstairs for gamma, although I had written index downstairs for alpha. Okay, I have reason to do that. I want to write down contravariant form for the gamma matrices. When I write down gamma mu, I would say gamma mu is gamma 0 and gamma I. Okay. As far as alpha matrices are concerned, whether it's a subscript or superscript doesn't matter, simply because alpha nu plus alpha mu gave you delta mu nu, and delta mu nu with indices downstairs and upstairs always gives you answer 1, so it doesn't matter. Okay, so that is not the case if you have a eta mu nu sitting in front. Okay, and that's what the gamma matrices would do. Okay, so once you define gamma matrices, then you can define a covariant form where 0, you write down gamma mu with 0 component being gamma 0 and spatial component is gamma I, and this would satisfy gamma mu is equal to 2 times eta mu nu. Okay, fine. Now, since we have chosen eta mu nu to be 1 minus 1 minus 1 minus 1, okay, so I'm sorry for choosing this. I defined it right in the beginning of this class, of this course, that I'm going to choose this metric. This is opposite of what I am using in the GR course, but since there are two different courses, let's not confuse this choice. Okay, but here we'll continue using signature 1 minus 1 minus 1 minus 1. But that tells us that if you substitute eta mu nu to be this quantity, then gamma 0 would continue to be Hermitian, but gamma I would be anti-Hermitian because gamma I would square to minus 1. Okay, is that fine? Any questions? You can just keep it on. Okay, if there are no questions, then we can kind of proceed ahead. Fine. So once you write down gamma matrices in this particular form, then you can replace. We of course know that if you multiply this equation by beta, there is a gamma 0 sitting here now because gamma 0 is same as beta, and a gamma I sitting here. or gamma vector, if you want to call it, which is beta times alpha. Because if you had multiplied the entire stuff, we had a beta here and a beta times alpha there. Okay, so now you have a gamma 0 and gamma vector going with del del t and nabla respectively. Okay, so you can write down this entire equation in a covariant form, which takes the form which is I times h bar times gamma mu del del x mu minus m times c acting on psi equal to 0. Okay, I have also done something in the process, that I have divided this entire equation by c, replaced ct by x naught, and instead of having mc squared, I have only mc here. Okay, so that is what happens here. Okay, and this is what is called the Dirac equation in a covariant form. Okay, any questions? Okay, so this notation can also be further simplified, and it's often used in lot of textbooks, a lot of books in fact, and that is to not write gamma mu del by del x mu or anything gamma mu multiplying something else, but write down gamma mu, any object O mu, to be O slash. Okay, and O slash is defined as gamma 0 O 0 minus gamma I O I. Okay, and for example, gamma mu del by del x mu would just be written as del slash. Okay, so if you use this notation, then the Dirac equation would just look like I del slash minus mc upon h bar acting on psi is equal to 0. Okay, so this is kind of a more economical way of writing down the same expression. It of course subtly, not subtly, but like, you know, I mean, it effectively uses the fact that it is gamma mu times an appropriate operator. Okay, but notice one more thing, that you get a factor mc upon h bar, which is the inverse Compton wavelength. It appears again. The square of this quantity had appeared when we looked at Klein-Gordon equation, but now you get exactly the inverse Compton wavelength. Okay, now remember that if you try to work in what are called natural coordinates, that means the coordinates in which you set h bar is equal to c is equal to 1. Okay, then in those set of coordinates, I mean, if you use that kind of notation, then in that notation, mass dimension is same as 1 over length dimension. Okay, and in that sense, this expression is consistent because a mass term is just 1 over the Compton wavelength. Okay, and that is how it appears in Klein-Gordon equation also, and that's how it appears in Dirac equation. So this is what I was trying to say right in the beginning, that it's not the de Broglie wavelength is important, but it's a Compton wavelength of the particle which is important when you want to ask when I want to do quantum mechanics in the relativistic setup. Okay, and in both cases we naturally encountered the Compton wavelength of the system of the particle. Okay.
So we
Yes.
haven't yet shown, right, that gamma mu behaves like a 4 vector.
Sorry.
We, like, in order to say that Dirac equation is covariant, we should be saying gamma mu is behaving like a 4 vector.
Yes, yes. I haven't shown that. Yeah, but it is true. Gamma mu transforms like a 4 vector. Yes, I will add those lines. Okay, but it is possible to check. You do a Lorenz transformation, you can show that gamma mu would transform like a 4 vector. Okay. Yes, thanks for pointing out. Okay, so coming back to what we are looking at, we can write down the Dirac equation for the conjugate wave function. Okay, and the conjugate wave function is not just psi dagger, but it is psi dagger times gamma 0. Now, this kind of way of defining conjugate object was something we had encountered even in the Klein-Gordon equation case. Remember, we had to write down phi bar, which was some phi times some quantity multiplying it. Okay, like in that case, it was just sigma 3. But uh, in this particular case, we have to take a 4 by 4 matrix if you are working in 3+1 space-time dimensions. Okay. this definition essentially takes care of the fact that gamma I are anti-Hermitian. Okay, so anti-Hermiticity would automatically be taken care of because every time gamma I runs across the gamma 0, it will flip sign, and after that, when it will act on psi dagger, because it is anti-Hermitian, it will give you opposite sign answer, but the anti-commutativity with gamma 0 will take care of that answer. Okay, fine. So the conjugated equation can be obtained by just looking at the Dirac equation and just take a dagger of the entire stuff. Okay. Now, when you take the dagger of entire stuff, then you need to be a little careful in this particular case because there are matrices sitting around there. Okay. So when you take a transpose of the entire expression, then the transposed expression would have alpha matrices sitting on the right, nabla acting on psi dagger dotted with alpha. Okay, similarly psi dagger with a beta on the right. Okay, that is just matrix multiplication rule. Okay, now you can convert this equation into the barred variable equation by multiplying by beta squared from the right in some sense. Okay, or maybe I shouldn't say it that way. Just on the right of psi dagger, you insert a beta squared. Beta squared is identity, so it doesn't matter really. Okay, but if you do that, then you can soak up one beta in the definition of psi bar. Okay, so psi bar is defined this way. So soak up one beta inside the psi dagger to write down psi bar, and second beta factor is the one that you keep. Okay, so for example, second beta factor that you have in front of psi, time derivative of psi dagger will give you gamma 0. The second beta factor in the spatial derivative with alpha factor will give you gamma I actually, although I have written it in this particular fashion. And the second beta factor here will just get rid of the beta out here. Okay, fine. So now you can clearly see that this equation can again be written in terms of in covariant form, and you can write down that as a Dirac equation for the conjugated variable. Okay, you may find a notation where you see I del slash acting on the left with the arrow pointing in that direction plus MC upon H bars factor. Okay, fine. So notice one thing, that there is a relative sign between these two operators. It is I del slash minus MC upon H bar, whereas that one is I del slash plus MC upon H bar. Okay, so in this case also you will find many places the notation having an arrow pointing to the right, indicating that this operator is acting on the right. Okay, there are some books which kind of meticulously keep track of this. Okay, fine. So we can use this equation to solve relativistic problems, or we can use this equation to take non-relativistic limit and find out what are the corrections that, say, non-relativistic Schrodinger equation would have. Of course, they would involve relativistic corrections, that means terms higher order in momenta and stuff like that. But it could also involve other corrections which are much more constrained in the relativistic quantum mechanics than in non-relativistic quantum mechanics. For example, the B dot L term that we had seen a few classes ago, that kind of coupling is kind of put in by hand in non-relativistic quantum mechanics. But in the relativistic case, you cannot put in things by hand. It has to have relativistic covariance, and relativistic covariance would dictate a class of terms that would appear in a given problem. And if you get B dot L term, then you get it. If you don't get it, you don't get it. There is nothing that you could kind of manipulate with the system and push in a interaction term that you would want. Okay, so the purpose of this, the reason why I'm saying that to find correction to non-relativistic equation is that the relativistic equation is highly constrained, and it will kind of give you a large, in fact, infinite class of corrections to the non-relativistic equation, of which of course we'll have to choose which are the dominant contributions and which are subdominant and or sub-subdominant contributions, which could probably you could leave out until you would probably want to do a more accurate experiment. Okay, so to do either of these two things, whether you want to solve this relativistic problem or you want to take the non-relativistic limit, it is convenient to choose a particular basis of gamma matrices. Okay, so this is what I was saying, that there is no unique basis for gamma matrices, and depending upon what you want to do, you could choose a basis which is appropriate for that computation. Now it turns out that for studying, say, relativistic quantum mechanics problems, or even to take non-relativistic limit, the Dirac's choice of matrices probably is the most convenient one. Okay. Hello, am I connected?
Yeah, we can hear you.
Oh, okay, good. Yeah, it showed my internet connection is unstable, so I was a little worried. Okay, so so Dirac's choice is the following: that you choose alpha matrices to be off diagonal, and off diagonal entries are just Pauli matrices. Sigma vector is sigma 1, sigma 2, sigma 3, which are the well-known Pauli matrices, and the beta matrix to be the diagonal identity and minus identity matrix. Okay, now this choice has naturally satisfies certain conditions. First thing is that alpha matrix is trivially traceless. Beta matrix is also kind of trivially traceless, where this 1 and minus 1 that I have written down are 2 by 2 matrices. Sigma are of course something we know that are 2 by 2 matrices. Okay, but nevertheless 2 plus 1s and 2 minus 1s here and explicit zeros diagonally, so therefore they are trivially traceless. Second thing that you notice is that both alpha and beta are Hermitian matrices, because Pauli matrices are Hermitian. And if Pauli matrices are Hermitian, then the way they are written in describing alpha, okay, under Hermitian conjugation, you would get this sigma vector coming and sitting out here with a dagger with it. So, and this sigma going upstairs with a dagger. Okay, so yeah, so alpha vector dagger would be 0, sigma vector dagger 0. But sigma themselves are Hermitian matrices, and therefore sigma dagger is sigma, and therefore you get alpha dagger is equal to 0, sigma, sigma 0, which is same as alpha. Okay, so that guarantees that alpha would be Hermitian. Okay, beta is Hermitian is kind of trivial, really no thinking is required. Okay, fine. So we can use this to write down gamma matrices. Okay, and that just follows from this rule that gamma matrices are gamma 0 is beta and gamma I is beta times alpha I. So just pick up this choice of alpha and beta matrices and write down gamma matrices in this particular form. Okay, and again, as I said, the sigmas are Pauli matrices. Fine. Now again, gamma matrices are also trivially traceless. Okay, and gamma 0 continues to be Hermitian. Okay, remember gamma I was not Hermitian, which is what we said at some point, because of this eta matrix relation. Gamma 0 is Hermitian, but gamma I are anti-Hermitian. Okay, so let's see how that works out. So you take gamma dagger, then you get 0, sigma dagger sitting here, minus sigma dagger sitting there, and 0. Okay, since sigma dagger is same as sigma, you get a 0, a sigma here, a minus sigma there, and a 0. So that tells you that gamma dagger is equal to minus gamma. Okay, and that's precisely the condition for a matrix to be anti-Hermitian. Okay, that under Hermitian conjugation it flips sign. Okay, so we see that this choice coming from the Dirac matrices naturally has anti-hermiticity condition. Okay, good. Now, given the fact that gamma matrices or alpha and beta matrices are written as 4 by 4 matrices, it is kind of natural that the spinor psi would have 4 components. Okay, so this 4 component spinor actually can be written in terms of 2 component polyspinors. Okay, so you can decompose these 4 component spinors into two component polyspinors, and then you can try to interpret these two different 2 component polyspinors. Okay, and the interpretation goes like this, that out of those two components, is there a question? Okay, so out of those two
Your
components, yes, sorry.
Your voice cut a bit, I think.
Oh, my voice is getting cut. Is it better now?
Yeah.
Okay. So what I was saying was that out of those 4 components, we can kind of show that 2 components describe the particle degree of freedom, of which one component is upspin component and the other is a downspin component, and the other 2 components of the 4 component spinor are the antiparticle degrees of freedom, again with spin pointing up and spin pointing down. Okay, so although Dirac wanted to get rid of negative sign in the dispersion relation, he could not get rid of the concept of negative energy solutions. Okay, because the spinor that he actually lands up with does have antiparticle degrees of freedom. Okay, fine. So of course he tried to kind of struggle with this particular solution, and he found that, like, of course mathematically it is impossible to avoid the 4 component solution, and it was impossible to also avoid getting the, I mean, what are called the lower components of the 4 component spinor to contribute with as a negative energy solution. Okay, which led him to basically postulate that there must be a particle with opposite charge and the same mass, and he called it a positron. Okay, so, and it was found, like, I think 3 years later. Okay, so let's try to look at current conservation. This is in this case we use the same technique that we have used in, say, non-relativistic problem, say Schrodinger equation, or even a few lectures ago when we used it in the Klein-Gordon equation. Namely, you look at the equation and multiply by a conjugate variable, and then subtract from it the equation for the conjugate variable multiplied by psi. Okay, multiplied by the original variable. So in our case, it will be psi dagger multiplying Dirac equation for psi minus Dirac equation for psi dagger multiplying psi. Okay, and this should give you, this should be equal to 0. That is how we are going to read out the current conservation condition. Okay, now remember that the equations take a form of this type, and if you subtract, so suppose you take this equation and multiply by psi from the right, and similarly if you take the other equation and multiply by psi dagger from the left, and if you try to subtract these quantities, what you would find is that the rest mass piece would just cancel out, and what you have is a piece involving the time derivative and a piece involving the spatial derivative. Okay, those 2 pieces you can collect and write them as total derivatives. Well, by total derivative I mean del t acting on psi dagger psi and nabla acting on psi dagger alpha psi. Okay, this form of the equation is very reminiscent to the kind of equation that we had when we wrote down, say, current conservation law for Schrodinger equation. Okay, and this is precisely the form that Dirac was actually looking for, because the 0th component of the current is psi dagger psi in this particular case. Okay, and therefore it is positive definite. Okay, and he wanted the rho part of the current to have a positive definite character, and that of course indeed is true in this particular case. Okay.
So,
Fine.
should it not
No.
be
Yes.
psi bar as in the case of, should it not be psi bar as in the case of, as in sine Gordon case?
Should we?
Should we put psi bar instead of psi dagger?
Here? No.
Yeah.
No. Here it is psi dagger only. Psi bar appears in the when you are looking at what is the conjugate variable. Okay.
Okay.
To put it a little differently, if you are looking at the behavior of the quantities in under Lorenz transformation, then a quantity psi bar psi is a Lorenz scalar. Okay.
Okay.
And whereas the quantity psi dagger psi is a component of a Lorenz vector. Okay. So in that sense, this is a correct object. If you try to write it in terms of psi bar, then you will find that psi dagger psi will be written as psi bar gamma 0 psi, right? Because you multiply by gamma 0 squared or beta squared, and then pick one beta and psi dagger and write that as psi bar. Okay, that was our. Okay, maybe I stay here. Where was I?
Yeah, I got it.
Okay. So I think it's kind of straightforward, but let me just show it once. Okay, so psi bar is defined as psi dagger gamma 0 or psi dagger beta. So what you could do is that you multiply by gamma 0 squared or beta squared here, and take one of them with the psi dagger and write down psi bar. Then you get psi bar gamma 0 psi. Okay. Similarly, you could put a gamma 0 squared or beta squared here and pull one beta with psi dagger and write down that as psi bar, and the other beta with alpha can be written as gamma vector. Okay, so now you see that this entire expression can be written as psi bar gamma mu psi. Okay, and that is a natural covariant form of a vector current. Okay, so therefore psi dagger psi is a component of a vector. Okay, whereas psi bar psi is actually a Lorenz scalar. Okay, and that's why we don't want psi bar psi sitting here. Okay, right?
Yeah.
Okay. Good. So Dirac precisely wanted this kind of conservation law because this would have nice probabilistic interpretation, and rho is kind of positive semi-definite, and everything kind of works out fine with this. Okay. But then there's a small problem with J. Rho is perfectly fine. J is a bit of a problem because J does not look like the J that we had in Schrodinger equation. Okay. In case of Schrodinger equation, J involved derivative of wave function. Okay. So therefore it looked like there was some kind of a velocity involved. Okay. Whereas this quantity, the J vector piece written out here, is just C times psi dagger alpha vector psi. Okay. That is the kind of expression. Okay. Now that is quite different, and what we could try to do is to try to interpret C times alpha vector to be the velocity operator. Okay, so we can call C times alpha vector as the velocity operator, and if you do that, then you can try to interpret J vector as kind of a current density. Okay, remember psi dagger psi would be like a charge density, and if you want to interpret this as a current density, you have to have some velocity factor sitting around, and therefore C times alpha vector is something that we want to interpret as a velocity vector. Okay, now that is fine. We can always kind of just by fiat define something as a velocity operator. Okay, but this velocity operator has a peculiar property. Remember, alpha has eigenvalue plus or minus 1. Okay, So therefore, if you ask what are the eigenvalues of the velocity operator, and the answers are plus or minus c. Okay. Now remember, we are studying a system of, we are studying an equation which is massive Dirac equation, right? We have a particle which has some mass m, right? This is the equation, right? Now, if a particle has mass m, you wouldn't expect it to have velocity either plus c or minus c. Okay, fine. You would be looking for velocity which is somewhere in between. Okay, velocity which is bounded by c. Okay, that is the upper limit that the velocity would have. Okay, but nevertheless, eigenvalues of c alpha are plus or minus c. Okay, and of course this leads to some other effect that one talks about, or rather one doesn't talk about really, called Zitterbewegung. Okay, Zitterbewegung is something which says that the way the Dirac fermion propagates is that it always propagates with, even if it is massive, it always propagates with speed c. It is just that it keeps zigzagging around on the light cone. Okay, so if you try to kind of say that it goes with velocity c in, say, in one direction for some time, you know, for, I mean, by some time I mean really infinitesimal time, and then it switches to minus c, and then after some point it switches to plus c again, and switches back to minus c, and so on. And if you kind of look at tiny zigzagging of this particle, okay, then and then you kind of try to ask what would be the effective path of the particle, you will find that that path is time-like. Okay, that path is typically inside the light cone. Okay, and so that was one of the interpretation that was given to the fact that this velocity operator has eigenvalues plus or minus c. Okay, we will not get into this discussion, but even current is interpretation of these, how the Dirac particle would actually move is through Zitterbewegung. Okay. Anyway, so but it doesn't concern us right now. Okay. Fine. So as I was saying some time ago, that you could just multiply this equation by gamma 0 squared sandwiched between psi dagger and psi, and kind of soak up factors appropriately. You can actually write down the current in a covariant form, which looks like C times psi bar gamma mu psi. Okay, and so this looks like a natural way of writing down a current, and a conservation of the current just tells you that del mu of J mu, which is a derivative with respect to the four-dimensional space-time, would be equal to 0. Okay, if you try to do that, then what will happen is that when you take a del mu of J mu, you basically get the Dirac equation satisfied by psi bar times psi minus the psi bar times Dirac equation satisfied by psi, and that is of course naturally 0. Okay, fine. So I think what I'll do is I'll stop at this point, and in the next class we will try to develop some understanding of the velocity operator. Okay.
Sir, can we say that two components
Any
represent
question?
a particle and the other two components represent
Sorry, can you speak a little louder?
Yeah, you were saying that two components of this spinner represent a particle.
Yeah.
And the other two represent antiparticle.
Yeah.
So can we separate them?
Well, yes. So the answer is that like you can separate them only when you are in the rest frame. Okay. Otherwise, you cannot separate them.
Okay. We can. I mean, we can work only with the particle component in the rest frame.
Yeah. Yeah. I mean, like what you will find is so we will see in maybe I don't know, maybe next or the lecture after that, is that the four component. Okay. Okay, let me give you an analogy. Okay, and which is what precisely happens in the Dirac equation, but it's easier to explain in the Schrodinger equation. Okay, So let's look at Schrodinger equation. And in the Schrodinger equation, you have, forget about say potential, just look at the free particle. And in the free particle case, if you look at the spatial derivative, you have second derivative acting on the wave function. Okay. So what you could do is you can say that the first derivative, spatial derivative acting on psi, let's call that psi1 is equal to psi2. Okay. And first derivative, spatial derivative acting on psi2 is equal to del psi by del t. Okay. Fine. If you try to do this, write down the equation in this particular fashion, then you can convert the Schrodinger equation into a two-component equation. Okay. And when you look at this two-component equation, you find that the upper component is the Schrodinger wave function, and lower component is the derivative of Schrodinger wave function with respect to space. Okay. Now, if you look at Schrodinger wave function for a particle which is at rest, okay, that means it has zero momentum, then the lower component would just trivially vanish. Okay, right? And therefore, you will get the answer which is only the upper component. Now, what happens in the case of Dirac equation is precisely that. You convert a second order equation into a first order form. And when you convert that into first order form, you get a 4x4 matrix, okay, and a 4-component solution. Of the 4-component solution, upper component is actually the wave function of the particle, and the lower component is the derivative of the wave function of the particle. So if you try to look at the particle at rest, then the lower component will just vanish and the upper component would survive. Okay. But what happens is that, like, apart from having this piece, you also have an antiparticle solution, which is lower component is a wave function and the upper component is a derivative of the wave function. And if the antiparticle is at rest, then the lower component is non-vanishing and the upper component goes to 0. Okay. Now, when I say upper component and lower component, I'm talking about two components actually, two upper components and two lower components. The two upper components are actually the polyspinors, which could be 1, 0 or 0, 1. The two lower components, say for particle, are also 1, 0 or 0, 1, but multiplied by a term which is like sigma dot p upon some factor like e plus m or e plus or e minus m, depending upon whether you are looking at particle or antiparticle. Okay. So, but because it is sigma dot p upon e plus m, when p is equal to 0, this piece will just vanish and only upper component survives. Okay. So if you have a solution written in that form, okay, then you would call that as a particle-like solution because that is related to beta matrix or gamma 0 matrix having upper component being 1 and the lower component being -1. So upper component has positive energy and lower component has negative energy. Okay. So if the upper component is non-zero and lower component vanishes in the non-relativistic limits, becomes small in non-relativistic limit, then you would call that as a particle degree of freedom, and upper two components are called large components, lower two components are called small components. Okay, if the situation is opposite, that the lower components survive and upper components become small, then it is an antiparticle degree of freedom, and you call the lower component large and the upper component small. That is how the solution turns out. Okay.
And this also happens in the massless limit.
No, in the massless limit, upper and lower component would just decouple.
Okay.
Okay, because remember the number of components of the solution itself is smaller.
Not say massless limit. Let's say we were traveling, we were in a frame in which the electrons travel close to the speed of light.
Yes. Yeah, but that is same as taking massless limit, because you see, if the momentum is so large that the velocity is very close to c, then the rest mass piece is so small that you can happily, to leading order, can just ignore it, right? So imagine, like, electron has a rest mass of say 511 keV, but total energy, like, if you accelerate it using applying electric and magnetic fields and so on, if the total energy of electron is like, say 1 TeV, okay, which is like, 10 to the 9 keV, okay, then 10 to the 2 keV compared to 10 to the 9 keV is like trivial number. You can, to leading order, just ignore it. Okay. And in that case, it becomes massless particle effectively. And in that case, you can in fact describe that particle as in terms of two component formulation. Okay. If you're working in 4 dimensions, of course. Okay. In fact, when you would do particle physics, you will learn that, that certain decays of, decays of certain particles are highly constrained, because in one form of decay, the outgoing particle is relativistic. In another form of decay, the outgoing particle is non-relativistic. And you get counterintuitive answers, but non-relativistic mode of decay is much more favored compared to relativistic mode of decay. You would have thought that, like, if something comes out with relativistic energy, the phase space volume available for such a decay is much larger. But in reality, there is some conservation law which forbids a relativistic decay. Okay, and that is simply because in the relativistic limit, instead of 4 component, you can happily work with 2 component wave functions. Does that answer your question?
Yeah.
So
Yes.
So we were trying to describe a single electron motion, right?
Yes.
So, I mean, right now we have psi as a 4 components object.
Yes.
And it does not typically, like, it does not transform under Lorenz transformation or anything. It's a Lorenz scalar, right?
No, it does. It transforms as a spinor, actually.
Like, what is that transformation?
Okay, so good point. No, I have not written it down right now, but okay, so I can tell you how it transforms. Okay, so what you do is the following: that you want to write down the Lorenz transformation matrix. Okay, now suppose you have a vector. Okay, say a mu. Then you know how a mu transforms under Lorenz transformation. Okay, a mu transforms by lambda mu nu a nu, right? That is how it transforms, right?
Yeah.
And lambda mu nu is typically antisymmetric in its indices. Okay.
Yeah.
Now, it just so happens that the vector mu also has 4 components. Okay, but those 4 components transform like a vector, whereas psi is a 4 component spinor and doesn't transform like a vector. Okay, so what you need to do is to ask, what is a matrix that would rotate components of this 4 component spinor? Okay, and that matrix can be written in terms of gamma matrices. Okay, so you write down a gamma mu and gamma nu and take a commutator of that. Okay, so if you write down gamma nu commutator, you get a new matrix. Okay, and that matrix acts like a Lorentz transformation on the components of spinor. Okay.
Okay.
In fact, you can kind of explicitly construct the Lorentz group representation theory as to how it acts on these spinors. And if it is not done, I would think that it would be done in quantum field theory course, but if it is not done, I can kind of try to do it at some point.
Yeah. Actually, my question was that we were trying to describe one electron system or something like that.
That's right, yeah.
In general, when we solve the Dirac equation, we'll get 4 components.
Yes.
How do
Hello?
Hello?
How do what?
Yeah, I was saying, in general, when we solve Dirac equation, we'll get some psi1, psi2, psi3, psi4 for all the 4 components.
Yes,
some
yes.
functional form
Yes.
for nt and x.
Yes.
So I was saying that the first 2 you said correspond to plus and minus spin of the electron itself.
Yes, yeah.
Since I mean, I would think that since there is no spin degree of freedom right now, those 2 will be equal.
Which 2 will be equal? No, no, no.
The first 2, like spin plus and spin minus.
No, no, no. Those
solution.
are no. In fact, the spin degree of freedom naturally comes out of Dirac equation, in fact. Okay.
Even without a potential, they'll be different.
Yes, they will be different. Exactly. Yes. Yes. In fact, of course, you would have gotten that from Lorenz group representation theory, but that is a separate point. If you look at Dirac equation, the spin is a natural outcome of it actually. In fact, as you can see that, see, if you are trying to study, say, the Schrodinger equation, then you would have to kind of write down this 1, 0 or 0, 1 component as additional spin or multiplying the Schrodinger wave function, and introduce Pauli matrices by hand, saying that, oh, there are some internal spin degrees of freedom for these particles, and Pauli matrices kind of tell you what are the eigenvalues corresponding to the spin degree of freedom. These Pauli matrices are naturally appearing in Dirac equation, embedded inside the gamma matrices. Okay, so it is not like you put them in by hand. You know, they are natural outcome of the consistent equation that you would write down for a spin half particle. Okay.
No,
So,
that is fine, but like suppose I have two electrons, one spin
yeah.
up and one spin down.
Yeah.
And I am studying its dynamics.
Yeah.
In a relativistic fashion.
Yeah.
And if I don't have a potential which interacts with the spin,
yeah,
like the plus or minus should not matter, right? The outcome should be same. Like observables should be same for the plus and minus spin.
that is right. I mean, if they have same momentum, then you know, you would detect.
Yeah. Everything else is same. But
Yes.
just that one spin, like one electron is plus and minus spin.
That is
but
right.
We are saying wave function will not be the same. The spinner
wave
component
function will not be the same. Yeah, exactly. So the scalar part of the wave function, that means the kind of Schrodinger wave function that you would write down, would be the same, but it would be either the first component or the second component, depending upon which is the spin projection.
Okay. And also, even for single electron, we are getting some antiparticle solution. Like there will be some non-zero components.
No. So that is what I was explaining to Harshit. You see, you can do that. You can do this even with Schrodinger equation. If you write that in a matrix form, then the lower component of the Schrodinger wave function, okay, is just the derivative of the upper component. Okay.
Yes.
So you can convert any order differential equation into a first order differential equation by converting that into a matrix equation. Okay. Is that fine? So you can write down, like, you know, suppose you have a 10th order differential equation, you can convert that into a matrix equation, and the column vector which is a solution to this is psi, psi prime, psi double prime, psi triple prime, dot 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 up to psi 9 primes. Okay.
Yeah.
And you can convert that matrix operator as a single derivative operator with some other entries such that the equation comes out right. Okay. So by doing this, you are not doing anything new. All you are trying to do is make the equation look like a matrix equation. Okay. But the second, third, fourth, fifth component of that column vector are not totally independent. They are related to some related to the first component through derivatives. Okay. Let me put it a little more physically. That would probably maybe more appealing. Suppose you look at Schrodinger equation. Okay. And when you are studying Schrodinger equation, then and suppose, you know, you have some potential and you are trying to kind of write down Schrodinger equation inside the in the classically allowed region. Wave function takes some form. In the classically disallowed region, wave function has some form, and then you want to kind of construct the full wave function. So what do you do? At the boundary of these two regions, you say that the wave function should be continuous. Okay. And you also say that the derivative of the wave function should be continuous. Right?
Yeah.
And the reason why you do this is because your equation is second order differential equation. So you need to impose two boundary conditions. Right?
Yeah.
So you impose these two boundary conditions and then you match your wave function. Now, it's the same problem that you are studying, but with relativistic variables. Okay. And you write down Dirac equation. When you write down Dirac equation, then your equation is written out here, which is just first order derivative, right? This is just a first order derivative with respect to time as well as space. Okay. So if it's a first order equation with respect to space, only condition that you can impose is that the wave function should be continuous across the classically allowed to classically disallowed region. Okay. But how is it possible that in the non-relativistic limit you have two conditions and in the relativistic limit you have only one condition? And the answer is that's not what happens. What happens is that in the relativistic theory, you have twice as many components to your wave function. Okay. And the lower component of your wave function is actually derivative of the upper component. And therefore, when you say that the entire column vector has to be continuous, implies that the upper component continuity tells you wave function continuous, and lower component continuity tells you that the derivative is continuous. Okay, and therefore when you take appropriate non-relativistic limit, it actually produces the same kind of boundary condition that the Schrodinger equation had. Okay, so this is just a mathematical trick of writing it in a column vector and imposing just continuity of the wave function, which of course carries the information about the derivative in the lower component. Does that explain the point a little better?
Sort of. So if, I mean, this Dirac equation is still a single particle equation.
It's still a single particle equation,
And
yes.
we'll use this particular equation both for electron and positron.
Yes. If
and
it is a
under like free particle dynamics,
yeah,
both electron and positron should behave similarly, I guess.
yes, unless you probe them, you wouldn't know, right? If you apply magnetic field, they would turn in opposite direction because they have opposite charges.
Yeah.
Right.
So,
but until you do that, you wouldn't know.
Yeah. So when we solve it, we'll at the end get some four component spinner.
Four component spinner, yes.
And that can be interpreted as the wave function of either an electron or a positron.
Absolutely, absolutely. So one,
regardless of the spin.
Yeah, you will get four solutions. One solution is electron with upspin. Second solution is electron with downspin. Third solution is anti-electron with plus upspin, and fourth solution will be anti-electron with downspin. That's how it will be interpreted. Okay. If you work in non-relativistic case, Schrodinger equation with polymatrices, then you will get two solutions. One is electron with upspin and electron with downspin. Okay. And what happens in the relativistic case is that the problem gets doubled simply because antiparticles also get in.
Even though we are studying an electron, like
even if you are studying only one particle thing. It's not clear that we are studying electron or not, right? We are just studying a spin half particle, really. That's all. Because until you detect it, until you have coupled it to electromagnetic field, you wouldn't know what is the charge or anything, right? No test is being performed on this object.
Yeah, okay.
Sir?
Yes.
How does it account for multi-particles? I mean, we have no bound on the number of particles if the particle is relativistic. Then how does this Dirac equation account for that?
Well, that is the reason why you need to do quantum field theory. Okay. What we are trying to do is to interpret this still as a relativistic quantum mechanics of a single particle. Okay. But for a free particle, of course, you could do this without much worry. But if you have an interacting particle, then that interacting particle could decay into multi-particle states if the energy is sufficiently high. Okay. For example, as I was saying that, like, if you have an electron whose rest mass is about 511 keV, if its total energy is like about a TeV, while propagating, it could just decay into electron positron pair, or it can even decay into electron plus proton antiproton pair. I mean, the energy is so much that it could just decay into a proton and an antiproton also. And of course, the process would lose energy. Okay, but if it has a 1 TeV energy, losing out 2 GeV worth of energy by producing a proton antiproton pair is no big deal for it. It would still have energy of the order of a TeV. Okay, so if there is an interaction, then of course such a thing would happen. Okay, this is one of the reasons why at such very high energies we do not actually produce the electron-based colliders. Electron-based colliders would lose a lot of energy because just too much energy is available for the interacting particle to decay into a lot of debris, and that would just contaminate the entire the experimental setup. That is the reason why one actually studies collision of only protons, for example, in say LHC in CERN. Okay. Of course, you can have a linear collider, which is what people are thinking about, as to have a linear collider of electron and positron to do more clean experiments. But most of the current colliders are circular, and you know that a circular collider means a charged particle is undergoing accelerated motion and would lose energy, synchrotron radiation, and various other energy losses. Okay. So, but the point that I'm making is that you can, of course, study non-interacting single particle system in relativistic setup, okay, which is what we are studying right now. But if you couple it to anything else, okay, then it has a potential problem of losing energy by pair producing something else or other, okay, and that tells you that absolute numbers of these particles are not conserved, and in that case, relativistic quantum mechanical description is not a very safe thing to attempt. Okay, and that necessitates elevating this entire problem to quantum field theory.
Sir?
Yeah.
Here in relativistic quantum mechanics, do we have that basis decomposition? Like any psi can be written as.
Oh, absolutely, absolutely, yeah, yeah. Hilbert space
Yes.
description is there, of course.
So in that sense, the first step of solving this equation was, I mean, fruitful.
What does that mean?
I mean, we have a basis now.
Oh yeah,
I
yeah,
mean,
definitely. Yes.
Yeah.
Yeah, true.
Because, sir, do we usually get free particles? I mean, I thought actually we don't have free particles.
Yeah. Well, I mean, the point is that, like, if there are free particles, you wouldn't know, right?
Yeah.
So of course, whatever you know is not a free particle. So sorry, it's a kind of odd way of answering it, but yeah, the thing is that, like, even if you have so-called free particles, as soon as you introduce theory of gravity, then they are not free. Okay, they at least gravitate, right? Even if they don't have rest mass, they would still have moving mass. They will have some energy, and as soon as it has even small non-zero energy, gravity will catch them, because gravity interacts universally. Now the point is that, like, if you say that, like, there is a body which is gravitationally neutral, okay, then boy, all bets are off. Okay, but that is what I was trying to say in the other class, in GR class, that there is nothing called a gravitationally neutral body. That is a part of the equivalence principle statement. But if there is a gravitationally neutral body, then you might as well believe in God, I think, then anything can happen. Sorry, jokes apart. But if there's a gravitationally neutral body, then there is really nothing which can, there is no experiment that we can do from whatever knowledge we have right now to be able and detect that object. Okay, so that object could just exist, and you will never be able to perceive it.
Sir?
Yes.
Research said that people like equations for quantum mechanics.
Yeah.
Schrodinger also started with a relativistic equation but couldn't work out something else.
Yeah.
Why didn't they like start away directly from a general coordinate invariant?
Oh well, yeah.
Lorenz invariance.
Yeah, they could have. Good question, but I think general relativity was looked upon with some suspicion for quite some time, actually. Even till kind of early 50s or something. I mean, you can easily imagine the following this thing, that with this kind of formulation of gravity, and with impeccable prediction about bending of light, which was detected in 1919, okay, 1919, kind of more than 100 years ago, you would have expected that Einstein would have got Nobel for doing that also, right? Second Nobel. Okay, it didn't happen till it died in 1955 or 56 or something, right? So clearly theory was kind of looked upon with some amount of suspicion, and I think one of the reasons why people did not want to do a most general coordinate invariant formulation was that there was a community which actually did not believe that this was really a correct formulation. I mean, that's my guess. I mean, whatever I have read seem to indicate that, but like, I'm not sure. But of course, special relativity was accepted by everybody by that time, I think.
Yeah.
Yes. Any other question? Okay, so if there are no questions, let me first stop the